Next problem. Let x of t and y of t both have zero mean and w is a random process. X of t and y of t mean are 0 and both are WSS process. Consider the random process z of t defined by z of t is equal to x of t plus y of t. First one, find the autocorrelation function and the power spectrum of z of t if x of t and y of t are jointly WSS. Second one, find the power spectrum of z of t if x of t and y of t are orthogonal. Third one, show that x of t and y of t are orthogonal. Then the mean square of z of t is equal to the sum of the mean square of x of t and y of t. We'll see the solution. Given z of t is equal to x of t plus y of t, that is equation number 1. First one, the autocorrelation of z of t is given by r z of t1 comma t2, which is equal to expected value of z of t1 z of t2, where t1 equal to t, t2 is equal to t plus tau. For our convenience, we are taking like this, right? Which is equal to expected value of x of t1 plus y of t1, because from 1 we know z of t is equal to x of t plus y of t. We are replacing here. So second one, x of t2 plus y of t2. So multiplying each and every terms, x of t1 into x of t2, y of t1 into y of t2, x of t1 into x of t2, and y of t1 into y of t2. So that is equal to, we are giving expectation to individual terms. So expected value of x of t1 into x of t2 plus expected value of x of t1 y of t2 plus expected value of y of t1 x of t2 plus expected value of y of t1 y of t2. Therefore r is z of t1 t2, which is equal to, so we are changing it into autocorrelation. First expected value of x of t1 x of t2, right? So t1 t2 r xx, both are x, r xx time t1 t2, right? Second one, expected value of x of t1 y of t2, so r xy t1 comma t2. Third one, expected value of y of t1 x of t1, r yx t1 t2. Last one, expected value of y of t1 y of t2 is nothing but r yy t1 t2. Given x of t and y of t are jointly WSS, that means r z of tau is equal to r xx of tau plus r xy of tau plus r yx of tau plus r yy of tau, that is 2 number, equation number 2. Taking the Fourier transform on both sides of 2, we will get, so we are giving Fourier transform to all the terms, the equation number 2. So Fourier transform of r ss of tau is nothing but s z of omega, right? We know Fourier transform of autocorrelation is the power spectral density. So r become s whenever we are taking Fourier transform, right? So hence s z of omega, which is equal to s xx of omega, s xy of omega, s yx of omega, s yy of omega. That is equation number 3. Given second one, x of t and y of t are orthogonal. So orthogonal means we know the condition r xy tau, which is equal to r yx tau, which is equal to 0. Then 2 becomes r z of tau, which is equal to r xy of tau plus r yy of tau. That is equation number 4, because remaining terms are all 0. So applying Fourier transform on both sides, now Fourier transform is nothing but the power spectral density. So it will become s. So s z of omega, which is equal to s xx of omega plus s yy of omega. Next, third one, given x of t and y of t are orthogonal, put tau is equal to 0 in 4. So r z of 0, which is equal to r xx of 0 plus r yy of 0. We know the result r xx of 0 is expected value of x square of t, that is mean square, right? Mean square of x. Ry of 0 is nothing but mean square of y. So expected value of z square tau t, which is equal to expected value of x square t plus expected value of y square t, which is equal to that means the mean sum square of z is equal to sum of the mean squares of x of t and y of t. That's all. We'll see in the next video.